This is Embedded Systems Design class, and as we talked in the last time, today we will introduce lecture 3, which is about the C language. First, let's talk about why the C language. There is certain criteria in the C language that makes it a best fit for the embedded or for programming embedded systems. Most programs for embedded system are written in C for the following reasons. Programmable or programmer productivity, indicating the number of debugged code lines produced per day. Its portability. The code can be retargeted to different processors. For its clarity, the C is easier to understand than assembly language. This is why we are moving to a high-level language. And it considered to be a modern compiler. Modern compilers produce codes that is close to manually tweaked assembly language in both code size and performance. And because of this point, actually the C language have some statements that are very close to hardware than any other high-level language. Now, the way that C is written can impact the assembly language size and performance. For example, if you have this data type, the unsigned integer 32, we know that the size is 4 byte. If it is used where an unsigned integer 8 would suffice, meaning only 1 byte is required, both performance and code size will suffer. Learning the assembly language or architecture of the target microprocessor provide performance and code size intuition for compiled C code. If you have a background in assembly language, it will help you write an efficient C code. Answering some of the these concerns or these questions, like does the microprocessor have support for multiply and divide? You only care about this if you have knowledge about the assembly language. Also, can it shift only one position or multiple positions? Meaning, does it have a barrel shifter or not? Another question, how much internal RAM does the microprocessor have? So you are aware that there's certain limits that you cannot exceed. Does the microprocessor have floating point support? If it doesn't, you cannot define a variable like float and double. So we will write our programs in C, but it's good always to have some background in assembly language. Sometimes you have to write assembly code for performance reasons, meaning you write a C language, you compile it, the assembly code is generated, and then after that you have to look through it yourself. Sometimes it's good to add things or update or modify some stated to make it better for your own microcontroller. Now, it's good to know the steps. If you have a C code, you do the compilation, or the compiler will give you an unoptimized assembly code. After the optimization step, you will have an optimized assembly code. Usually it's have this extension .s for assembly. To understand the difference between optimization and or an optimized code or unoptimized code, here's an example. After compilation of those two statements, you have I, J, and K variables. So what happens is for every statement, you have two instructions. You move the value of J to the working register, and then you do the addition. Again, here, you move the value of J to the register, and then you do the addition. Notice that we use to move for the same purpose, where there is no need actually for the second move instruction. And this is the part that is done in the optimization. You take one of these instructions out. That's just an example. After you have the optimized assembly code, you do the assembly, and that's the job of the assembler, where you have after that the machine code or the .o code. After that, you do the linkage. You link some other libraries, and after that, you have the executable, usually in .hex. But basically, it's zeros and ones. Also in C language, we have the following types, 6 types to program our microcontroller. We have the unsigned character, the unsigned integer, the unsigned long, the signed character, the signed integer, and the signed long. They can be defined as you can see here. This is the unsigned integer 8, meaning 8 bits or 1 character. Unsigned integer 16, meaning it's a 16-bit or 2 byte. The long is the unsigned integer 32, which is basically 4 bytes. This is the unsigned version for it, and this is the signed version for the same number of bits. So it's good to know that there's actually difference between the unsigned and the signed representation. The signed value is assumed if there is no modifier presented. In the signed value, we usually use the 2 complement representation, and basically this is happening in all the digital machine. For the signed, they use the 2's complement representation. Now we have arithmetic operator in the C language. We have the addition, the subtraction, the increment, the decrement, the multiplication, the division, shift into the right, shift into the left, bitwise and bitwise OR and bitwise XOR, and we also have the bitwise complement. It's very important to know the symbols as well. So let's start with the bitwise logical operator. Assuming you have these 2 values, the K is 0x2f and the I is 0x61. If you do the bitwise AND operation, we simply rewrite the hexadecimal representation into binary. So if you do the bitwise AND between the I and the K, this is the I, this is the value, this is the value of K, which is 2, and F, and here we have the value of I, which is 6 and 1 in binary. We do the AND, we do it bit by bit. This is what we mean by bitwise AND operation. So you do it bit by bit here. 0 ANDed with 0 is 0, 1 ANDed with 1 is 1, and basically it's always 0 except if you have 1 and 1. So it's 0 here, here you have 1 and 1, so you have 1. The rest is 0. Now for the OR operation. For the OR operation, this is the sample. Again, we do the OR. The OR, you will have 0 only if it is 0 and 0. Otherwise, you will have 1. So 0 and 0, you have 0. 1 and 1, you have 1. 0 and 1, you have 1. 0 and 0, you have 0. And the rest is 1 since you have 1s in one of the variables. The XOR operation denoted by this symbol. And the XOR, if they are the same, meaning 0 and 0, or 1 and 1, you will get 0. If they differ, you will get 1 in the output. So whenever you have difference in the value, you will have 1. Here you have difference in these two or these 3 bits. So you'll have 1 and 1 and 1. Now for the bitwise complement, the complement means that you get the inversion of every bit. So the 0 will become 1, the 1 becomes 0, the 0 become 1, and so on. This is the definition of the bitwise logical operation. These are the 4 important ones. Now, let's say you were asked to clear a group of bits. To do that, you need to specify 2 items or 2 things. First, what's the operation that you are supposed to use? And what is the appropriate mask? So first you have the operation. Second, you have the mask. Since you want to do this operation, clearing a group of bits, let's say you are supposed to clear the upper 4 bits of I, and I is this value, and this is J, and this is K. So we want the 4 bits, these 4 bits, which is here, of I. If we write down I in binary, we want to clear these 4 bits, which is 0, 1, 0, 0, which is 2 in hexadecimal. To do this, you need the appropriate mask for it. So you need to have zeros in the position of the bits that you want to clear, and then you add them with the zeros. For the other bits, you will AND with 1, since ANDing with 1 doesn't change anything. So here we ANDed with 1, meaning 0 and 1 is going to be 0. This is the same. We just copy this one here, since you are ANDing with 1. And ANDing with 0, here you will clear the upper 4 bits. So there will be 0, 0, 0, and 0. And the result of ANDing hexadecimal value 0xC2 with the mask 0xF0 is going to be C and 0. Notice that we kept the C, but we zero out the 2. Kept the C here, and we zero out the 2. Okay. So now we know that the appropriate mask is supposed to be 0xF0, which is this one in binary. As a rule of thumb, for the AND, or the bitwise AND operation, if the mask bit is equal to 1, the result bit is the same as the operand. If the mask bit is 0, the result bit is cleared. Now, let's have another application. Let's say that you want to set a group of bits. And let's say that those bits from bit 1 to bit 3. You have to be careful about this. When we number the bits, we usually start from 0. So you have bit 0, bit 1, bit 2, and bit 3. That's the first hexadecimal digit. And then you have 4, 5, 6, and 7. That's the second hexadecimal digit. Now you want to set bit from B1 to B3, which is these 3 bits. You want to set them, and the others, you don't want them to change. So now, since you want to set, you will choose the OR operation, or the bitwise OR operator, and you will have this mask where you have 3 ones whenever you want to set, and zeros in any other bit. So now you will have these 3 bits, since you are bitwising with or you are bitwising with 1, then you will have the 1, 1, 1, and the rest, they will be the same. So they are the same. And again, the reason for that The mask, when you have an OR operation, the mask, if the mask bit is equal to 0, the result bit is the same as the operand. And if the mask bit is equal to 1, then the resulting bit is going to be equal to 1. Another application, let's say you want to complement, not the whole number, but a group of bits. So now we want to complement bit 6 and 7. Oh. If you have the value k, this is 8 in binary, and this is 8 in binary. If you want to complement only bit 6 and 7, meaning these two bits here, then you need to do the XOR operation, or the bitwise XOR operand, with ones at the bit positions where you want to complement. And that's a property of the XOR. Know that if you have an XOR gate, and you have, for example, X, and the other input is 0, here, let's have the same input, and the other input is 1. If the other input is 0, then the result is going to be X. If it is 1, then the result is going to be X bar, or the complement of X. So whenever we want to complement, we use the XOR operation, and we put ones in the places that we want to complement. And you can see here, the 0 becomes 1, and the 1 becomes 0s. The rest of them, they are the same. So the appropriate mask is 0 and C in hexadecimal. For the XOR, or the bitwise XOR operand, if the mask bit is equal to 0, the result bit is the same as the operand. If it is 1, then the resulting bit is complemented. Now, let's say you want to complement all the bits. Now, this is easy because you will just use the complement operator. And here, if we take k, the complement of k is going to be, you flip all the bits, the 0 becomes 1 and the 1 becomes 0, or what we call the ones complement. All right. Now, after introducing the bitwise operands, and now we will move to the status register, because every instruction will affect the status register in a certain way. Some instruction not going to affect any of the status register bits. Some of them affect some bits of the status registers bits, and others, they affect all of them. Anyway, the status register is a special function register, like the working registers, for example. And this is the status register. As you can see, we have 0, 1, 2, 3, 4, 5, 6, and 7, and another 7 bits. So in total, we have here 8 bits and another 8 bits. So it will be 16 bits. But actually, the high byte, we don't use any of the bits except one, which is this one here. We have C for the carry, Z for the 0. We have OV for the overflow, N for the negative, IPL012 for the interrupt priority level, and the DC for the decimal carry. In this class, we are not going to discuss the DC because this is used for the binary code decimal, and we are not going to talk about this in this class. Some bits that we should mention here is the overflow bit. Only this will be flagged, or its value is going to be equal to 1 if you, in your operation, your current operation can generate or generated in an overflow. If the value is negative, then this flag will equal to 1. This RA here is the repeat loop active. The RA bit is read only. It's sent, this will be set to equal to 1 when you have a repeat instruction, or that your repeat instruction is active, and it's cleared when the repeat instruction is finished. Uh, the IPL is 3 bits, so you can assign an interrupt priority to any method, any function in C, starting from 0 all the way to 7. And we will talk more about the interrupt priority level when we talk about interrupts later in one of the modules. Other than that, we have the carry and the 0, and we will specify this further next. Bit 0 of the status register is known as the carry, or the carry flag. Bit 1 is the 0 flag. If you have an instruction, and this instruction could generate a carry, you should worry about this flag. If the carry flag is equal to 1, this means that you have a carry generated. Similarly here for the 0, if the value is equal to 0, the flag will be set. If you go to the table and the data sheet of all the instructions, you can see for each instruction what bits of the status register are affected. Here is a snapshot of this table for the add operation and for these two move operation. For the add, if you have add F, meaning that F is equal to F plus the working register, this is the number of words and the number of instruction cycles for these instructions that it have. And here you have the bits that are affected by the this instruction. Since it is add, it could have an overflow. It could have a negative value after you do the addition. It could have a 0 after you finish the instruction. Similarly, it could generate a carry or a decimal carry. For this move, since it's only assigning F to a working register, there is no status bits in the affected column. And for this one, where you move F, meaning that you move F to you do the assignment again. For this, you could have the negative or the 0 flag. So if F is a negative value, once you assign it, this will be raised, or this flag will be risen. Similarly for the 0. But since this is only a working register, it doesn't affect the status register. Now, we move to the other operations. We talked about the bitwise operations. Now we will see the shift. We have a logical shift to the right. And the logical shift to the right, simply you shift the whole or the bits, if you have a byte from bit 0 to bit 7, to shift it to the right to this direction, you will add a 0 at the most significant bit, and you drop the P0. Now, if you want to do a logical shift to the left, now you shift to the left by 1 position. Here, you will add a 0 in the least significant position of the result, and you drop the or bit number 7. Now, notice here in the right, we say it's a logical shift. But in the left, we didn't specify any type. The reason for this is the following. We have actually 3 different type or two different type of shifts. We have the logical shift and we have the arithmetic shift. Now, the logical shift to the right is different than the arithmetic shift to the right. But for the left, if you are shifting to the left, the logical and arithmetic is going to be the same. To see this better, here's an example. Now, if you have a logical shift to the right, what you do is you introduce this 0 to the most significant bit, and then you drop the B0, similar to what we explained here. You introduce the zero and you drop the B0. Whether it's 8-bit or 16-bit, it's the same scenario. You drop the B0 and you introduce 0 to the most significant position. For the arithmetic shifts, you don't add 0. You actually add the last bit in the most significant bit again. So you conserve the sign. If you have an arithmetic shift, we worry about if the number is signed or unsigned. So if the number, we assume since it's arithmetic, the number should be signed numbers. And the signed numbers, if you have 1 at the end, it means it's a negative number. So you shift, you add the most significant bit again. If it is 1, meaning a negative number, you add it again. If it is 0, meaning it's a positive number, you add it again, whether it's 8-bit or 16-bit. Now, for the left, if you are shifting to the left, it doesn't matter whether it's logical or arithmetic, because you will always have 0 introduced in the least significant bit, which doesn't indicate the sign like the right. And because you have it here, you just drop the last bit. To understand this better, here's some examples. Let's say you have these 4 variables, I1, K1, I2, and K2. I1 and K1, they are unsigned, while I2 and K2, they are signed. Notice in these statements, these C statements, you have logical operations, either shifting to the left or shifting to the right. Which one of them is logical and which one is arithmetic? The only way to know this is by knowing the type of the variables. So if you are working with I1 and K1, like here and here, then these or this operation is logical shift. If you have I2 and K2, since they are signed numbers, then these two are arithmetic shift operation. So let's see the example. I1, 0x, FFFF. Now we know that it's unsigned. So this is logical operation. To shift it to the left by 1 position, FFFF, you will introduce 0 here, and you will shift the whole thing to the left. So what happens is, let me expand this a little bit. So you have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and 1, 1, 1, 1. This is the value of I1. So to shift it to the left by 1 position, you will introduce a 0 here, and you will drop this one. So you will have 0, 1, 1, 1, which is E, and the rest will be F, F, and F. Now for the I2, now this is an arithmetic shift to the left. And we know that the arithmetic and the logical, they They don't, there is no difference in the mechanism because you will introduce always 0 at the end and shift to the left. Now, how many zeros you introduce is 5 zeros, since the amount of shift here is 5. And because of this, you will have 0 here and followed by E. Now, for K1 and K2, we know K1 is unsigned, so you have a logical or shift to the right, and K2 is signed, so you have an arithmetic shift to the right. And to do the shift here, you introduce a 0, since it's logical. So the value of K1 is 255. 255 is actually, notice that K1 here and K2, both of them are 8 bits. So K1 is 0x F F. This is the value of K1 in hexadecimal. So you shift it to the right and you introduce 0 here. The result is going to be, and you can pause the video here and try to get it yourself if you want. And the value will be, you add a 0 here and shift it to the right. So it will be 0x 7F, or equal to 127. Now, in K2, it's a signed number. So this is an arithmetic shift to the right. Now we know that K2 is equal to -1. K2 is equal to -1, which is in hexadecimal, is going to be F. Remember, you have 1. In 2's complement, what you do, you go to the right most position or the least significant bit. You find the first one and then flip the other bits to get the 2's complement. So if this is equal to 1 in decimal, this will be -1 in decimal. So we know that -1 is equal to 0x FF, which is this one. Now to do the shift to the right, and it's an arithmetic shift, you go find the most significant bit, which is this one, and then you add it again to the right, which means the result is going to be equal to the same, 0x F and F. Now, we will move to the conditional tests. We have many operators like the equal, the not equal, greater than or equal, less than or equal, the logical and, the logical or, and the logical negation. You have to be aware of their counterpart in the bitwise operation. So we have the bitwise and, the bitwise or, and we have the complement. In a conditional test, we have the logical and, which is you have this sample 2 times. You have this sample, the same as the bitwise OR operation, but 2 times. And we have the this sample for the logical negation. Now, if an operator used in a C condition test, such as an if statement or a while statement, return a non-zero value, then the condition test is true. So you just look at the value. Is it 0 or non-zero? If it is non-zero, then it's true. If it is 0, then it's going to be false. Let's look at it further. This is the difference between the logical negation and the bitwise complement. So if you say not I, and your I value is 0x0 A, since this is a logical negation, this value is non-zero. So if you take the negation, it would be a zero value. Now here we have a complement. If you have this value, you complement every bit. This is a bitwise operation. So the 0 will become F and the A will become 5 because the zeros here, 0, 0, 0, 0. The complement is 1, 1, 1, 1. And for the A, which is 0, 1, 0, 1, the complement would be 1, 0, 1, 0. And this is actually 5. So be aware if you are looking at a logical negation or a bitwise complement. You have to differentiate. Similarly, if you have a bitwise AND or a logical AND. So in this example, we have a logical AND. You have I and J. So you check the value of I, you check the value of J. For this if statement, you will uh, uh, execute the statement between the parentheses only if I is non-zero and J is also non-zero. But if you do the bitwise operation, you just perform the bitwise operation. You find the value of I, the value of J, and you do them bit by bit. Here are two examples. If you have A, I, and J, as you can see here, if to do the bitwise operation, you simply calculate the value here in binary, just to make it clear. The B is 1, 1, 0, 1, 0, 0, 0, 0. This is for the value of J. The value of I here is 0, 0, 0, 0. And the A is 0, 1, 0, 1. Now, to do the bitwise operation, this is the bitwise operation, and here you have a logical AND. To do the bitwise operation, you just do it bit by bit. 0 ANDed with 1 is 0, 0 and 1 is 0, 0 and 0 is 0, 0 and 1 is 0. Similarly, for the 4 bits, it's 0, 0, 0, and 0. So the result is 0x, 0, 0. That's for the bitwise operation. For the logical AND, or simply we call it AND, this is I and J. For that, you would say that J is non-zero value, I is a non-zero value, so the result would be also non-zero value or true. It's stored in the memory as 1. Okay. What about the OR? Similar scenario. If you see the comparison between this and this, the only difference is the operator. Here, in the bitwise operation, the result would be 0x B and A. Again, if you get the A in binary, 0, 0, 0, 0, 0, 1, 0, 1, and the J is 1, 1, 0, 1, 0, 0, 0, 0. And now you calculate the bitwise OR operation. This is the OR operation. 0 and 1 is 1, 0 and 1 is 1. Here you have 0, and here you have 1. Here's 0, 1, and 0, and 1. And this is A, and this one is B. You can do it also in the hexadecimal level, if you like. For the OR operation, since you have one of them is non-zero value, then the result is non-zero, indicated by this one. Actually, if it is any value, it's going to be correct except 0. Now, let's have some examples for the equality, the inequality, the logical, the bitwise logical C test. So for this here, you have A is equal to 5, B is equal to 10, and you get these variables as the results. A is less than B. Since A is less than B, it's true. So the result is equal to 1. They are not equal, so the result is 0 or false. Here, you have the result A is greater than B is false, and A not equal to B is true. So notice that the true and false, we indicate them and when we have the assembly of our microcontroller, it's written in the registers as zeros and ones. We don't have a Boolean uh, uh, type. So if it is 1, it means it's true. If it is 0, it means it's false. Now let's see the other ones, the other exercises here. Let's say that A is equal to 0x0f and the B is 0xf0. And you are doing a logical, or sorry, you have the logical AND. For the logical AND, A ANDed with B, since this is non-zero and this is non-zero, the result is going to be true or 1. Here, since this is the OR operation, it's the logical OR operation, the result also true. We need only one of them to be non-zero. We have both of them actually non-zero. So the result is also true. For or not B, this is the logical negation, the result would be, since B is non-zero, so the opposite of that is going to be 0 or false. Now, how about the AND? If you do the ANDing, the bitwise AND for these two, the result is going to be 0. And that there is a difference between both of them. If you do the logical AND and the bitwise AND, this one gives you the result equal to 1, while this one gives you the result equal to 0. For the OR, if you do the bitwise OR, the result is going to be 0xf. Here in the bitwise negation of the variable B, it would be 0, 0. So you need to be aware of the logical conditions and the bitwise operations. You have to differentiate between them. And now we will move through the statements in C. Most of them you already know, but we'll go through them one by one. The F statements, you have F followed by a condition, and be aware of the syntax. So you have F and you have a condition and you have an F body. After that, you have else and you have else body. The F body will be executed when the condition here in the condition test is non-zero or true. The else body will be executed when it is 0 or false. Also be aware that you can have many if else statements, and we can see this in the following or in a future slide. So let's talk about some of the things that you need to be aware of in the if statements. You could say that if statement like this, if and not I, then do this job. This means that it will be executed, the F body would be executed only if I is equal to 0. You could also rewrite this like this, I equal 0. It has the same meaning. If you have like this example, you have Fi, and you have certain statement here, it would be executed when I is not equal to 0. So any value of I, whether it is 1, 2, 3, 5, any value other than 0, it will you will execute this value. And you can rewrite this as I not equal to 0. And this leads us to the next slide, which is actually, you need to be careful when you are working with the if condition. Be careful of the assignment and the equality test. So for the equality test, if I is equal to 5, you will uh, uh, execute this statement. Otherwise, you won't execute it and move to the next statements in the code. So you will only execute this if I is equal to 5. But here, if you by mistake forget one of the equal signs, meaning it becomes an assignment, this would be always true because 5 is non-zero and you assign it to I. So I is a non-zero value, so you will always execute this statement. If you have another example where I is equal to 0, so now if instead of 5 you have 0, it would be always not true, which in turns you will, or because of that, you will never execute the statement in the body. So for this example here that you see in the slide, I is equal to 5, and you will always execute this statement because this is an assignment. So you need to be aware of this. Now, we said that in the if statement, you could have only one else or multiple of them. So here, if you have f, for example, if I is equal to 1, do this. Else, other than that, if it is equal to 2, then do another thing. Else, if it is equal to 3, then do another thing. And the last one, if it's none of the above, then you do the last statement. And now notice that we are doing this one by one. So we moved here. If it doesn't work, then you move to the second stage, you move to the third stage, and then you end up with the end. We can rewrite this instead of chained if-else structure, you do it with a switch structure, where you have a switch, you switch based on the I value. The I value is the one that makes the decisions. You have different cases. In case I is equal to 1, then you do this. If it is equal to 2, then you do this. If it is equal to 3, then you do this. This is only happening because you are including a break right after each case statement. So you have a case statement, and then after that you have a break. Another case statement, then you have a break. Another case statement, you have the break. If it's none of these, then you have the default value, and you will have this statement. If you don't have this break, for example, in case of, or in the case I equal to 1, it will execute this statement, and then it will jump and execute the next one. To make sure each case has its own statement, then make sure you use break at the end. The last statement, the default, you don't have to follow it by a break because you are at the end of the switch. When you're done with this one, it will, you'll finish with the switch. Switch is more organized than the if-else, as you can see, and it's very a good way of coding. Now moving to the loop structures, starting with the while. You have a while. It's very similar to the if. The only difference here is that you will do this over and over again as long as the condition is true. So whenever the condition is true, you keep looping in the while loop. If it becomes false, we get out of the loop and do the rest of the code. Here are some examples. If sum is equal to 0, I is equal to 0. Let's initialize them first. While I is less than 10, then the sum is equal to the sum plus I. This is the running sum of I. And then you increment I and so on. You keep doing this as long as you are having the value of I less than 10. So starting with 0, you keep adding 1, 2, 3, all the way to 9. Now at this iteration, I is equal to 9. 9 is less than 10. You go and sum up the 9 with the rest of the numbers. And then you increment it. It becomes 10. If you go back, is 10 less than 10? No, you get out of the code. And this code will have the sum of the numbers from 0 all the way to 9. Now, this is another example. Now you have a logical add. If I is less than 100, or the sum is less than 1000, you keep looping. Sorry. If both conditions are true, meaning I must be less than 100 and the sum must be less than 1000 for you to keep looping within the while. If any of them failed, you get out of the loop. You started with 0. So you have 0, 1, 2, and you keep summing. You keep the running sum here. As long as I still less than 100 and the sum is less than 1000. Try to write down this in MPLAB and see what's the result of the sum. Now, for the for loop, the for loop is very structured. You have a for, you have a statement here, another statement, and a third statement between the parentheses. So you have 3 statements. This one will be executed only once before the test. And then you have the condition that you need to check. And then after that, you have the body of the F to execute. And then when you exit the for loop, you go back here and you execute this statement, which is the increment. To understand the for loop better, let's rewrite the for loop into while. So you have this one executed only once before the while, and then the condition, while this condition is true, you do this if or the for body statement, which is this one. And then after that, you do the increment, and then you keep looping. So for this example, this statement executes 10 times. And they are both equivalent. Now, let's move to a subject that you might face in the C language, which is the array and pointers. The pointer is a variable, or a pointer value is a variable that contains the address of another value. So it's actually pointing to that, or pointing to this data. The array is a collection of elements. And you can move through the array either by using an index or by using the pointer. And this is why we have these two associated with each other. So an array is a collection of like elements, such as an array of integer, array of character, and so on. One use of pointer variables in C is for stepping through the elements of an array. Another way of doing this is using the index, as we mentioned. So let's have some example to understand this better. So let's first look at the pointer and how to work with them. Let's say that you have K and J as unsigned integer 16 variables, and you have a pointer. You define it this way by adding this star. So if you have it this way, this definition means that A is a pointer. The variable A is a pointer. So looking at the memory here, before executing the third statement, after executing the third statement, and after executing the fourth statement. So in the first two, you just assign value to K and J. And this is why you have the value of K here and the value of J over here. In the third statement, what happens is A is equal to the address of J. This is the address of J. Meaning now A before execution, the third statement has nothing. What you should do here is the address of J. Now I have the J here, and the address of J is this one. So you write down the address of J for the A. Now, in the fourth statement, you say K is equal to whatever is A pointing to. This means that the pointer of A is actually J, where a copy of you copy J to actually K. So how to do this? We'll go here. Now the value of K, it originally before the statement for, it has this value. Now what you do is you say, okay, I need to get what is the value that A points to. The value that A points to is this one here. So you copy this data and you put it right. In general, if you have this sample, you say this is the address of. So A is equal to the address of J. If you see this value, it's a dereference operator. K is equal to the pointer A means K equals to what A points to. So in this one, A is here, and it points to this value. So K is equal to whatever A is pointing to. Now, after understanding pointers, how to define them, how to work with them, now let's see the relation between the pointers and the array. At the beginning, we will see array of an unsigned integer 8 variables. So here we have 8 bits, and we have 4 different values. Each one of them is 8 bits, like you see here. And memory, they will look like this. Again, the width of the memory here is 16. So we have here 50, we put it here, followed by PA, followed by 27, followed by 63, since it's little Indian in our macro control. This way we define X before executing the first statement. Now, after executing the first statement, you say, notice that we use the indexes of the array to know which member we have. At the beginning, I should mention that this 4 here is the size of the array. Here, the size is 4, so you say 4 here. Now, whenever after the definition of the variables, if you have numbers between the brackets, it's indicating the location of this variable within the array. So here we say, okay, x1, where is x1? This is x0, 1, 2, and 3. These are the indexes that you have here. Index 0, index 1, index 2, and index 3. Now we say x1, which is this value here, should be assigned to this location, x2. So you should move this one here. And this what will happen in the memory. You copy AB from here and you put it here. Now, after that, in second statement, you'd say that y, which you define as a pointer, is equal to the address of x2. So y has nothing here. Now you go to x2. This is x2. You check its address. This is the address of x2. And you put it right there. And after this is the third statement. You say y plus plus or increment the value of y. Now we know that y is 0x208, and you increment it to the next position. Now the next position is going to be 0x3080. How did we increment? From here to here, it's kind of obvious to you now because you have 802 plus 1, 803. But there is a catch here. When we say y plus plus, it's actually y plus 1 times the size of the type that you have. The type here is 8 bits or 1 byte. So the size of this one is 1 byte. 1 times 1 is equal to 1, and you just add 1. So 802 becomes 803. But if you do have the same code, the only difference is now the size is 16. What will happen here? Now the variable, we have different variables here since it's 16. We have 4 variables. Each one of them is 16 bits. This is why we have them this way. And you fill them one by one right there. And you do the same thing. The only difference here at the third statement, notice in the first statement you did x1, you copy it to x2 here. And here you assign y as the address of the x2, which is x2 here. It's 0x8 or 408 in hexadecimal. So you copy it or right there. Now what happens when you increment, it's not going to be 805. It's actually 806. Why? Because now we have the size of the unsigned integer 16, which is 2 bytes. So now you add by, or you increment by 2. And it's also obvious when you see the locations. This is 16 bits. Each variable will accommodate 2 bytes. So you will have the starting one is 0x008. And remember, we said that the variables and the microcontroller start with this position. We can put the first variable here. So you have 0x008 accommodating 2 bytes. So the next one would be at 0x802. The next one, 804. The next one, 806, and so on. So when you have a pointer pointing to a certain location, if you increase this pointer, which is y, you increase by, or you increment by 2. That's the idea here. Let's give you now more examples about the usage of the C language. This is the array sort example. It's 2 nested for loops. When you have an array, generally, to go through the elements, you write it down this way. You would say 4, and then you define an index, let's say I, and then you say I is equal to 0. Let me start from the first position. And then you go through the elements of the array less than the size of the array. Let's say size. Of course, you need to define I and the variable I and the variable size before the for loop. But after you do this, you do then increment I++ to go through the elements, and then you do the work that you want to do within the array. So usually it's like this. For I is equal to 0, I less than the size, I plus plus. Usually whenever you are working with the array, it goes this way. Here you can see that we do 2 for nested loops for two nested for loops. The first one, I is equal to 0. You start with the index I for the first 4. I is equal to 0. I is less than the size, but it's the size minus 1. Let's see. Y minus 1. And then you increment the I. For the second for loop, you started, your index would be j. You didn't start from 0. You started from I plus 1. And here you have the j is less than the size, which like what you expected, and then the j plus plus. Now here you should have two questions. Why the minus 1? And why you started the j with I plus 1. And you have if statement. If I of, or the array A of I is less than the A of j, then swap them together. Swap the I, the two elements with each other. So to understand why we have minus 1 and why we have I plus 1 here, let's draw this table. We have the index I starting with 0. Notice the j here, we started with 1. Because if we started with 0, the comparison would be between A of 0 and A of 0. And this is meaningless. Why would you compare something to itself? You should compare it to the next position. This is why you have the j equal to I plus 1, which is the next position. So if you start with I0, the first j that you will compare with is the next one, which is 1. Here, if you have 1, the next one is 0. Here, if you have 2, the next one is going to be 3. Here, if you have 3, the next one is going to be 4. This is how you compare. Now, what happens here is you compare these two positions first. Notice that I have A0, A1, A2, A3, and A4 in this example. If that's the size that I'm going to use, which is 5, from 0 to 4. You compare between these two. Now, the condition says if A of I is less than A of j, then you would swap. And because of this, now you compare A of I, in our case, A of 0, which is 8. Now we have 8. And A of j, which is 1, we have 3. 3. Now, if 8 is less than 3, is 8 less than 3? No, you wouldn't swap. So actually what I should have here is greater than. Instead of this one, I have greater than. So based on the condition, either you swap or you don't swap. So I stand corrected here. If A of I is larger than A of j, then you do the swap. And we do this because we want to sort in an ascending order. If we do the other way around, it would be the descending order. Anyway, let's continue with this. Now you have 8 and 3. If A of I, which is A of 0, is larger than the A of j, which is A of 1. So now you have 8 and 3. 8 is actually larger than 3. And because of this, you need to swap. And this is what we did. We did this swap indicated by this symbol. Now what you do after that, you increment the j. So you compare the same position, a of 0. We still add the a of 0 with the a of 2. So you compare the 3 and 5. There is no problem here. And then you increment the j to the next position. You compare the 3 and 1. Now 3 is actually larger than 1, so you need to swap. And this is what we did. And the last place we compared the 1 with the we compared this one with the 7, and actually the 1 is not larger than the 7, so we keep it the same. So if we stopped here, did we sort the array? Is it like 1 and then 8, 5, 3, and 7? No, we didn't sort it. We still need to work on the other position. But now we made sure that we have the correct number in the first position. And we can now worry about the rest. So in the first iterations, going through the j from 1 all the way to the last member, which is 4, we compared the first position with all of them, and we made sure that the least value is in the first position. And this is actually why we have the nested for loop. So we have to go through all of the comparison for the first position. And then again, we do this for the second position, for the third position, and for the last position. This is why we have the for loop. Now, now we answered this question, why we start with j is equal to I plus 1, because we don't want to compare I with itself. We want to start from the next position. Now, why do we have the buffer size -1 for this for loop? To understand why, we go to the first iteration again. And you can see here that we go from position number 0 and we compare it to 1, 2, 3, and 4, going through the first for loop. And then again, we will end, now when we increment the I, we increment by 1 position. So we move from here to here. Now the value of I is equal to 1. And then we do the same thing. And after that, we increment it again. It becomes 2. And we do the same. And then we increment the I in the last iteration, 2, 3, and we do the same. And notice that we increment it 0 to 1, 1 to 2, and then 2 to 3. We don't have to do another one from 0 to 4, like the j. Since we have 0, 1, 2, 3, and 4, we stopped actually at 3, and we result with the result was the sorted array. So let's go to the second iteration. The second iteration, now the value of I is equal to 1, because we increment the I. And now we compare this position, which is the first position, with the next one. 5 with the 8 with the 5, we need to swap. Now compare the 5 with the 3, we need to swap. Now compare the 3 with 7, we don't need to swap. And now we know that the 3 in the right position. We move to the next one. Now the I is 2. And we compare it with the next one, which is the 3, the index 3 or the position 3. 5 and the 8 and 5. 8 is larger, so we swap. And then compare the 5 with the 7. You don't need to swap, and the 5 in the correct position. Now notice the last iteration here. You just do one comparison between the 8 and the 7, and you fix both positions. And that's why we don't need to do another iteration. From 0 to 3 is enough for us. But that's a good example for any actually uh, high-level language, which is the array short. Now let's look at more functionalities of the C language. Here we can define the compound data with different types. So you can do it by using the structure or struct, and you give it a name, a date. And between these samples, you have whatever types that you want to define. Since it's a date, we have the month, day, and the year. The month and the days, unsigned integer 8 is enough because we know that the month is, we have only 12 months, and the day we have up to 31 days. But for the years, we have as much as we can. So this is why we define it as 16 bits. Now, to define a variable, let's say the variable is date or X or Y or Z, you define it this way with the type that is composed of two words, struct followed by the name of the type. Struct a date, and then you say date, and now you can assign the value using the object-oriented programming method. Date dot month is equal to 1, date dot day is equal to 18, and date dot year is equal to 2018, for example. This is to do the structure. The C language is very powerful to the point that you can assign up to the bits. So you can do this with the usage of the column. You can say here, you have flags. Integer f has only 3 bits. The unsigned integer f2 have only 1 bit. And for the f3, it has 2 bits. And for a certain value, let's say this value, f1, if we say f1 is equal to -2, and f2 is equal to 1, and f3 is equal to 2, f3 is here, right here, so 2 is 0 and 1. f2, since it's only 1 bit, and we chose 1, so it's 1. f1, we say it's -2. We know that the value 2 is 0, 1, 0. To get the minus the decimal value -2 in binary, we use the 2's complement, so it's going to be 0, 1 followed by 1, and this value is recorded here. So know that you could specify the number of bits by using the column value in the structure. More, we have the union, which is basically defined like the structure. You have union, and you have the name. Let's say I and C. I is 32 bits, and we have a character, or you could say unsigned integer 8. It's the same as the character C. And we defined 2 variables. You could have stopped it and define it similar like this one. You could have did the definition like this. Or you can define right after this sample and before the semicolon. And like here, we have my flags. You define it this way. Here, we defined ELT1 and ELT2. And in the union, the difference between the union and the structure is listed here in this table, where the structure, the keyword is struct, for the union is union. In the structure, the size, the memory is allocated for each member by itself. For the union will, the size of the union will be equal to the size of the largest member. And the reason for this is the next point, the memory sharing. The structure, you don't have memory sharing. In the union, you can share the memory between the members. So now you have I and C. I is 32 bits, C is only 8 bits. If you say now I is equal to 4, it will assign it as the value 4. C is equal to A, or the character A. So you see what is the character A in binary, and it's assigned its value there. Now you, at the end, you say that this value or ALT2 is equal, or dot I is equal to this value, meaning that it will overwrite what you have for the C. So you have DE here, followed by DA, followed by EB, followed by F and D. To understand this, now the C would be here only for 2 hexadecimal digits or 1 byte, and the I accommodate the whole space. So what happens if you specify the I, it will fill up the space. If you specify only the C, you will have the value of C right here, and the rest would be padding. Anyway, usually when you work with C, usually we use structure more than the union. There are few application for the usage of union. Now, moving to more concepts about the C language. The C language, as any other language, it uses subroutines, where instead of having instruction 1, instruction 2, and then you have A1, A2, all the way to AN, and then another instruction continuing from 1, 2, 3, 4, 5, and then again you repeat the same ones here. Instead of repeating or replicating the instruction sequence, what happens? The repeated part, we put it in a method with a return, and we call this the caller. So now in the caller, you call the callee or the subroutine. So you call the subroutine. The callee here is name is sub. So you call it, you go through the instruction, and then you return. When you return to the next instruction, and you continue. You have another call, and so on. So that's the idea of the subroutines. And here is a quick example. This is for the general C, not for our microcontroller. So you include a library. It's called the standard input output. And you have this function prototype or declaration. You declare that you have a method coming is called a square. The return value for it is float, and it accepts as an argument or parameter another float value, which is x. In the main function, you define m and n as float numbers, and you print a message, enter the number, /n is the new line, and then you read the number from the keyboard. Again, this is the general C language. We don't have a keyboard in the microcontroller when we talk about embedded system and microcontrollers. But if you have a keyboard and you want to read a value, you read it this way using the scanf method that is defined in this library. Whenever we use microcontrollers, we don't use this library because we don't have a keyboard, nor we have a screen to print messages on. So now you scanf. Scanf, F stand for formatted. So whatever print you have, it's formatted. Similarly for the scan. Here we have percent F, meaning you expect a floating point number, and it gives it, you give it at M, which is the address of M. So now you will give it the value, and it will put it in the memory in that address. And then you call the method that we have its prototype. You should write the method itself, which is the square. You can see that I copied this line right there. The only difference is now we have a semicolon. Here we open the body of the square, and you define another variable like b, and b would be x times x, since you are doing the square, and you return the value of b. Now here you just call it. You call the square m, whatever m that you read from the keyboard, you give it to the square subroutine or method or function. Usually in C, we call them function. So you calculate it, you return the value, and the value assign it to n. Now, if you want to print a message, the result is whatever value that you got here. So you would say the square of the given number is something, which is %f, %f. So what you are doing is the square of the given number, which is m. So this m would be here, is the result n would be here. The value here is the percentage for formatting it. This is a long story. You could write actually any number, decimal, float, hexadecimal, binary, octal, and there is many symbols that you can use instead of the F, but that's another subject. So in general, if you have subroutines, let's say that for this subroutine, you want to count the ones bits in an unsigned 16 parameter or an argument. You have this function. It's called count ones. This is the prototype of the function. This is the declaration. So you expect that it would be defined later here. And you have the main function where you have k and j. Let's assign value k with a certain value. And you want to count the ones within the k. You count the ones, whatever this method works out and give you the result j as an unsigned integer 8. And then you print it. You print the results by using printf. The number of ones or the 1 bits in this value, which is a hexadecimal value, the k. This is why we have %x, is %d, which is the decimal value of j. Now, how to find j? By having or looking at count ones. So here we have the argument v. So now we test v if it has 1, or how many ones you have in this variable v. So what happens here, we should go through all the bits of the this value, which is 16 bits. So we have from 0 all the way to 16. You have to move through them one by one. This is why we use a for loop. So you start from position 0 all the way to position number 16, and if every time you increment the index I. What you do, you test if v, the value that you got in the argument, ended with 0x1000, meaning you are only interested in the least significant bit. If it is 1, then you add 1 to a counter that you define here. Now you check the least significant bit. What you want the next position of v. So to compare to the next position of v, you do a shift to the right by 1 position. And you keep doing this for the next position and so on. To do this for our example, I'll do it for the first few bits to understand what's going on in the for loop. Here we have 1 0 0 0 0 0 0 0 1 0 1 0 and 0 1 0 1. So the number of ones is supposed to be 1, 2, 3, 4, 5. The return value in J is supposed to be 5. What you start with, you start in this position here. So the I is equal to 0 in this position. You compare this with this value, which is going to be 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And obviously, if you do that bitwise, and the result is going to be equal to a non-zero value. The non-zero was equal to 1. And because you have an if statement, you will increment the counter. So you accounted for this one. After you accounted for this one, the next thing that you will do, you will shift this value to the right by 1 bit. So you will drop this one, and you'll add 0 here. So you'll end up with 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0. And you do the same with this one, and you compare with this position, it will be 0, and you keep shifting. So you'll be interested in the next one and the next one, and you keep shifting until you account for all of the bits, and you count the ones. This one. This is the usage of the subroutine. So we have also in C macros and inline functions. The macros is the uses of hashtag define. So here we say hashtag define, the default baud rate is some value. Also, we have define, and we define a certain name. You choose led one, indicating a led that can be on and off. It has light, either if it is on, the light is or the lid will be illuminating the night. If it is 0, it's going to be off. There is no light. So you have a lid, you call it lid 1, and you define it to be underscore RB15. This is very important for us in the microcontroller, but we will discuss this in detail in there when we talk about the general purpose input output, or the GPIO. This basically indicates that you have bit 15 of port B connected to led number, but we will go through this more later. And here we have an inline function. The inline function is basically, instead of doing the prototype or the declaration, and when you the one that we described in the subroutine, if the function is very small, instead of doing a prototype and declaration and then you define it later like this one, so instead of doing a declaration and then define down here, if the function is very small, you right away do the declaration followed by the function itself. This is only recommended if the function is very short, like this. So you do it by writing static inline. If the compiler see these two words, it means that what follows is a very small function that will be declared, and also you write the function itself after that. And here we have this function. It's called configure the board B in bit 1 as a digital input, and you do it this way. This will be also important to us in the GPIO when you talk, or when you work with the trace value. This is a tri-state buffer. The tri-state buffer of port B in bit 1 is equal to 1, meaning that you are indicating that B, the port B, bit 1 is an input. And when you talk about the B, C, F, G, this is the analog. If it is equal to 1, it means that the analog value of this bit position, or for that pin, is going to be disabled. But we will talk more about this when we talk about the GPIO later. The interest here is the usage of the macros. by hashtag define, and the inline function by having static inline keywords. Now, the structure of the C program, as we mentioned, you have a preprocessor command. You have the type definition. You have the function prototypes for the declarations, and then the variables, and then also the function. Any C program must have the main function. It must have the main function. So that's what we usually have in the C program. So let's have some exercises. I believe we have 3 exercises, and then we will finish this lecture. So in the first exercise, we have this requirement, right? A C function to return the minimum number of an array. You have an array pointer, and as in the list, and you have the length indicating the length of the array. So to write this method, it's very simple. Actually, you need to return a value. I've used 32-bit. Here we didn't indicate, but for this method, we use 32-bit. Sometimes based on the compiler, either you have this type, integer 32, sometimes you need to add _t. Just be aware of this. If you use integer 32 and the compiler generated an error for you, then add _t and see if this fixes the problem. So here you have the array, and you have the pointer to the array as an argument, and you have the length of the array. You define a minimum and an index C. The minimum is the first member at the beginning initially, and then you go through the members starting from 1 all the way to the whole array 1 by 1. If the current member, which is array of C, the current member that you are working with is less than the minimum, then it becomes the minimum. You go through all the elements. Once you're done, you will have the absolute minimum of all the elements, and then you return this value. So that's basically an easy function. I suggest that you write this in the MBLab, compile it, and check if you get the correct results. Here you are asked to write a C function that shifts the bits in a 100-byte array A to the left. So the whole array, you shift it to the left in this direction. So the array A, if we have A0 all the way to A99, this is a 100-byte array. If you have these values, hexadecimal values, the binary for each one of them is indicated here. If you want to do shift to the left to the whole thing, what happens is at the end here, you will introduce a 0, and then you will shift all of the values. So here you can see that we shifted the 0, 1, 0, 1, 0, 1, 0, 1, and then 0, 1, 0, 1, it becomes here 0, 1, 0, and then this one, it was shifted right here. And you continue doing this. This will be shifted right there. Whatever value here, we don't know exactly what was it. So this is why I have a dot here. And the value here, 0, becomes here. And the value here, 1, it becomes here. And now you're done. This is what we want to do. We want to shift all the elements. So instead of, because we are working with an array, we have to go through the elements one by one. And to do this, this is what we've done here. This is the method. It's called shift array left by 1. We had the array as an argument, and that's another way of passing the array to methods. That's one way, and the other way is what we have here using a pointer. Either you use a pointer like this one, or you use the brackets indicating it's an array with its length as well. So these the two arguments. You go through all the elements, starting from 0 all the way through the length of the array. And the length of the array, of course, is going to be 100. And what you do is you have the current element, which is A of I, and then you shift it to the left by 1, because we want to shift the whole thing to the left. So for the first element, you shift it to the left by 1. Now, what you do, you will take the next element, because here, remember, we need to worry about the shift between the members. So if we start from A0, that's the first element, and you have A1, the second element, you want to do the shift to the left. What we did is we need the one from the next element, and we need to shift it right here. For the first one, we just shift it to the left. Now, if you shift this to the left, you will introduce 0 here. And that's not what we want. We want the one that comes from the next element. To do this, we will have it by using this. So what we did, we have A of I, the current member. We shift it to the left by 1. And then we OR it with the last bit of the next element. The last bit of the next element is indicated by this one. This is the next element, A of I plus 1. And then we shift it to the right by 7 bits, dropping all the bits but the last one. And then you OR them together. You OR them together. And to make sure that you're getting the correct result, we also add it with 0x 1, 0 to get only that bit. This is actually redundant. If you didn't use it, that's also fine. To understand what's going on here, let me do it for the first two elements, A0 and A1. For this one, we have B0, and for the next one, we have 1, 8. So let me do it here. We have B0, and we have the next element, 1 and 8. So what happens for this one, you shift it to the left by 1 bit. So you introduce a 0, and it becomes 0, 0, 0, 0. And then you have 0, and then the B, which is 1, 1, 0, and you drop the last one of the B out. This is after executing this. So it would be 0, 0, 0, 0, 0, 1, 1, and 0. But this is not exactly what we want, because we have a problem with the first bit. We need the bit that is in the last position in the next element. Here we have 1, 0, 0, 0, and then the 8 is 0, 0, 0, 1. And notice that we have 8. We have in the 8, we have 1 here, and we need it to be right there. To extract this one, what we will do is we will shift this value to the right by 7 digits. So we will drop this, and this, and this, and this, and we will introduce 7 zeros. So it'll become 1, 0, 0, 0, 0, 0, 0, 0. And now this value here, which is this one, we OR it with this value. As I said, we have a redundant calculation here. We can have this one, this value, and we add it with 0x10 just to make sure that we are interested only in this. And then we OR it. If you OR it, you will end up with the result between the ORing those two values, these two values, which is going to be 1, 0, 0, 0. 0, 1, 1, 0. So in hexadecimal, this is 1 and this is 6. And that's what we expect in the result, 196. And we keep doing this for the next values. You might think that this is the correct result. However, always when you work with arrays, be aware of the boundaries. If you keep doing this until you reach to the last element, this is going to be a of I. And you don't have ai plus 1. So for the last element, it won't work. And this is why we updated this to its correct version. This would be wrong because there will be a problem in the boundary, as mentioned. And this is why we don't go all the way to the length. We go to the length minus 1, and we do the same. And for the last element, we just do the shift to the left by 1 digit because we can't access there is nothing in the next element. And we are done. For the next C code in this tutorial, we are asked to write a C code for the following function. The function is called swap odd even, and it has one parameter a, which is the array of the of certain bytes, and you want to swap the odd and even elements by swapping their location. This is an example to understand better what's the requirement. If this is A0, A1, all the way to A99, with these 6 values, what we want the result to be the swapping between these 2 values and so on. This is actually easier than the previous question. We don't have to work with shift. We don't have logical shift operation here. We just simply do the swap for each element. So you go through all the elements from 0 all the way to the last element of the array, and you do the swap. We have 2 things that we need to worry about here. First, the increment. How did we do the increment? And also, how did we do the swap? If you have a of I, and you have a of I plus 1, to swap them, if you write the value of a of I plus 1 right away here, you will lose the value of a of I because you will overwrite this value. So what you do, first, you need to introduce a temporary value, and you assign the value of a of I to the temporary value. That's the first thing that you need to do. And then you can move a of I plus 1 to a of I. And now you don't lose a of I since you already have it in a temporary value. The third task is to have the temporary value in a of I plus 1. And this is exactly what we did. This is the first. We have the temporary value is equal to a of I. The second, we have a of I is equal to a of I plus 1. And the last statement, you have a of I plus 1 equal to the temporary value. That's the first part, the swap part. Why did we increment by 2, not by 1? The reason is, as you see here, what you want to do, you want to exchange these 2. Once you do the exchange, you swap them, you move to the 2 next elements. So you have, if at the first iteration you are at A0, at the second iteration you should be at A of 2, and so on. If you by mistake made it I plus plus or I plus 1, you won't have the swap. You will swap and then change, you will swap and then change, and the result will be a little bit weak. And you can try this in the MP lab. Now for the last task in this tutorial, this actually question is very close to what you will see in the next lectures. It's very close to the microcontroller and how to program the microcontroller. Here we say the write a C program for seat belt alarm system. The system generates a sound alarm when the driver sits on his seat for 1 minute without fastening his seatbelt. So when the driver sits on his seatbelt for 1 minute, the alarm sounds. Now the alarm duration is only 5 seconds, not like cars. Right now is the alarm is going forever. But here we have, or it's like a weak system. So the alarm duration here is only 5 seconds. The requirement here is sketch the state machine of the program and then implement it using a C code. And basically, this is the idea of the last tutorial number 4, to show you that by using the state machine, you will make writing the C code really easy. Here we have 2 inputs. It indicates the inputs. You have sit and fasten. Sit indicates that the driver is in his seat. If it is 1, the driver is there. If it is 0, the driver is not there yet. Fasten, does he fasten the belt or not? If it is 1, he fastened. If it is 0, he didn't fasten the seat belt. And assume that you have the following the following function. These following function later in the course, we will define them and how to implement them. But for now, it's given to you. These functions, starting the timer, is it expired or not? It returns 1 if it is expired, 0 if not. Also 2 action functions, starting the alarm and stopping the alarm. Now, the state machine is based on the states that the driver is on. Are you waiting for some event or not? So you will have states indicating the system, and you will move from one state to another state based on the inputs that you have. And here we have 2 inputs, the sit and fasten. So for this problem, you sit down, think about it a while, and then you can come up with the state diagram or the flow diagram that you see here. The beginning, the first state, you can name it anything, but here I give it a meaningful name. In the first state, you wait for the driver to get in. So if you are in this state, it means that you are still waiting for the driver. So now if you are in this state and then set becomes 1, meaning that the driver is, he sits on his seat. You move to the second state, which is waiting for 60 seconds. Why do we need to wait for 60 seconds? To see if the driver fastened his seat belt or not. Because this is the requirement and the problem. It says that the system generates sound alarm when the driver sits on his seat for 1 minute without fastening. So the system gives the driver 60 seconds without sounding the alarm, without doing anything. Once the 60 seconds passed, now we sound the alarm. So you wait 60 seconds, and if the 60 second is expired, you go to the next state, which is waiting for 5 seconds, which basically for the alarm, This is why when we move from here to here, we start the timer because we want to count 60 seconds. Again, from here to here, we start the timer because we want to count 5 seconds. We also start the alarm because moving to this state means that the driver is in and we waited 60 seconds without fastening the seatbelt. And this is why we wait for 5 seconds. And then after waiting for 5 seconds, you move to the other state, which is waiting for the driver to get out. Once he gets out, meaning that the set is equal to 0, you go to the original or the initial state. Notice that when I draw this initially, I didn't work this arrow or these two arrows out. It comes while you are thinking about the flow diagram. For example here, and it's actually based on the inputs, for every state, worry about both inputs. Here, if we have a driver, then the set changes. If the set changes, you go here. If it didn't change, meaning the set is equal to 0, you go back to the same state. Now, what about fastening the seatbelt? The driver is not there yet, so the fasten input doesn't indicate anything here. This is why we go to the next one. Now here, you could talk about the set. Did the driver still there? Or maybe he get out. If he gets out, you go back. But in this system, we work on the general case where the driver sits in and then he drive for a while, more than minutes, and then he comes back. So in the system, here, if you are waiting 6 seconds, you worry about the second input. Did he fasten or he didn't fasten? If he fasten, it means everything is fine. We don't have to sound the alarm. And we go to this state, which is waiting the driver to get out. Now, if we are waiting for 5 seconds, and while we are waiting, he fastened, meaning he was forgetting about fastening his seatbelt. The alarm sounds, and now he's aware that he needs to fasten the seatbelt. So you go to, you're waiting for the driver out, and then you stop the alarm. If he didn't fasten and the 5 seconds expired, either way, you stop the alarm. And this is why this system is kind of stupid, because right now at this point, he doesn't care about the driver, whether he is having his seat belts on or not. And while you are waiting for the driver out in this state, you only care about the set input. When it's becoming 0, meaning that the driver is out, you go here. You could add those two arrows, this arrow where the set is equal to 0. Similarly here, if the set is equal to 0, it's actually everywhere. Whenever the set is equal to 0, you go to the first state. But this is kind of an overkill of the system. If you do it this way, that's going to be enough. Why do we need the flow diagram? Why do we need the state diagram? The reason is it makes writing the code really easy. And you can see it in the next 2 slides. First, we need to include some libraries. Since this is going to work with the microcontrollers, as I said, this tutorial is very close to the microcontroller codes that we are going to show from now on. We include the BIC24 generic library, and we include the BIC24 specific for your own microcontroller. These libraries should be auto-generated by the MB Lab. You also have the functions that we give in the input, and we also will describe them later in the course. Either we will describe them or some methods that's very similar to them. So now you have the function headers. You need to define the following. We define the two inputs and we define the states. We have two inputs, set and fasten. We said that the first input is RB1 and the second input RB2. So we have two switches, R in port 1 bit number 1 and port B bit number 1 and port B bit number 2. For this one, it's going to be the set. For the second one, it's going to be the fasten. Now we can use set and fasten in the code instead of underscore RB1 and underscore RB2. For the states, we just give them the name, wait in, wait 60, wait 5, and wait out, and we give them random numbers. Could be any integers, 0, 1, 2, 3, or any numbers. And then we define this state. We say that it's unsigned integer 8 because it could be only one of the 4 states indicated by these numbers, and we call it state. Now to write the main code, we will make use of the flow diagram or the state diagram. Now you will see the mapping between the state diagram and the code. First, you have a main code. You say that this current state now is any of them. But initially, we would use the first one, which is wait underscore m, the one that we defined here. Remember, these are the 4 states that we have. So you say wait n is equal to the current state, which is state. And then you go through a while one, which is always true. And then you switch based on the current state. Either it's going to be wait n, or wait 60, or wait 5, or wait the driver out, or wait out. So you will have 4 cases for each state that you have in the state diagram. And now each case will end up with a break. Each case end up with a break. Each case end up with a break. Similarly for the last one, it will end with a break. Now, usually in every case, you will have an if statement based on a certain condition. And this condition is what the input tells you in the flow diagram. So if you are in this state, if you are in wait n, and the set is equal to 1, then you need to move to the next state. So there is an if condition, and the result of this if condition, the state will change. So the state goes to wait 60. Similarly, if you are here in wait 60, and you have a certain condition, the result of this condition that you will change the state. The state becomes wait 5. If you are in this wait, and based on a certain condition, you will move to the next state, which is waiting out. If you are in the wait out and you have a certain condition, you will go to the next state. So indicated by these arrows, these 4 arrows, each one of them will be these changes of states. Now, let's look at the details one by one. If you are in this wait state, wait n, if set is equal to 1, which is this, then you need to start the timer. This is what we did, and change the state from here to here, meaning the state is equal to wait 60. That's it. Now, for the next state, wait 60. To move from here to here, you need the timer to be expired. So if the timer is expired, you passed 60 seconds, you will start the start the timer, start the alarm, and change the state from this to this. So you start the alarm, start the timer, and change the state from here to here. Is that the only arrow that comes out of this state? No, we have another one. So we need to write its own if statement for it. If you were in wait 60 here, so this is your case. If the fasten is equal to 1, then you move to state equals to wait out. Now for the last state, or the last two, the wait 5, you are here. If the timer is expired, it's more than 5 seconds, or the driver fasten his seatbelt, meaning that his fasten is equal to 1. This or that, both of them, you will go to the same state, which is state equal to wait out, and also you need to stop the alarm. And for the last one, if you are here and waiting the driver out and the sit is equal to 0, then the state will be wait in. So you can see the mapping between the state diagram or the flow diagram and the code. It's very important to know how the code works. So the code works, let's say that there is a driver or there is a car without a driver. What happens in the code, it will go here. Initially, it will be waiting for a driver for this state. Is the set is equal to 1? No, there is no driver. So it will break and go again. Check, wait, break, go again. Check, wait, break, and go again, and so on, until a driver comes. Once the driver comes, it will go, oh, the set is equal to 1. So I will start the timer and go to the next state. Now the driver there, he didn't fasten his seatbelt. And we just started the 60 seconds. It will go here. Is it expired? Did he fasten? No and no. Go back again. Is it expired? Did he fasten? No and no. Go again, and so on. Until one of the events happen. Whatever the event happens, the instruction that follows it will be executed, and then you will go to the next state, which is waiting 5 seconds. Waiting 5 seconds, now the alarm is sounding, because the alarm is sounding here, unless he fastens his seatbelt. Now, is the alarm expired, or did he fasten? If any of these happens, you stop the alarm and move to the next state. If you are in this state, and the driver is driving somewhere very far, that he spent maybe 1 hour from point A to point B. During this 1 hour, it will always go. Is the driver out? No, it will break. Is the driver out? No, it will break, and so on. It keeps doing this until the drivers get out. Once the driver gets out, it will go back to the initial state. And with that, it marks the last tutorial of dealing with the C language. Now you should have good experience with the C language statements. Also, the last tutorial that we described is very close to the microcontroller. Usually we have flowcharts like this or state diagram, and we convert it to codes. And other than that, we will start next time by describing the PIC24, the pin diagram, the GPIOs. We will describe things that we just mentioned here. What do we mean by this? What do we mean by this? And so on. So we will work with the GPIO at the beginning, and then after that, we will talk about the timer. So it will show you how to work these functions, and so on. So at this point, we will move to modules. We already described the microcontroller. We defined the embedded system. We see the C language and how to work with it. And we also discussed the CPU, the program memory, and the data memory. And at this point, we are ready to jump to the modules one by one. Once we finish all the modules, we're done with the class. So next time we will start by the first module, which is the GPIO.